Hello, welcome to Basic Electronics Engineering course. This is the third lecture in the series of Basic Electronics Engineering. Myself, A. Venkat Subbareddy, Assistant Professor, Electronics and Communication Engineering Department, G. Pullareddy Engineering College. So, in this session, I will discuss about the PN junction diode, its symbol, and working of PN junction diode. So, in the previous session, I discussed about different types of semiconductor, that is intrinsic semiconductor and eccentric semiconductor. So in the eccentric semiconductor, two types are there. One is N-type semiconductor and the another is P-type semiconductor. So in the N-type semiconductor, which is formed by doping fifth group elements to the pure semiconductor. It contains donor ions, majority charge carriers are electrons and the minority charge carriers are holes. So this is the representation of N-type semiconductor. Similarly, the P-type semiconductor, which is formed doping of pure silicon or germanium with the third group elements. So it has represented by using acceptor ions. So because these are the third group elements, they are accepting one electron, so they will become an acceptor ions. It contains holes as the majority charge carriers and electrons are the minority charge carriers. So this representation will be used for explaining of PN junction diode working. So the holes are represented with this small dot, small circle, and electrons are represented by using a small dot. And acceptor ions, they are represented by using minus symbol. It is surrounded by a circle, and donor ions, they are represented with the plus symbol surrounded by circle. So if in the formation of PN junction diode, both these P-type and the N-type semiconductors are used, and these two semiconductors are placed nearer to each other, then it will form a PN junction diode. So that is, this is one of the pure silicon crystal, and it is divided into two equal parts, and one side it is doped with a P-type semiconductor, on the other side it is doped with the N-type semiconductor. So the separation between P and N side is called as an junction. So by doping P and N side to the pure semiconductor, that is that silicon or germanium, so it will form a PN junction diode. So it will contain majority charge carriers on the P side as holes, and the minority charge carriers are electrons, and on the N side majority charge carriers are electrons and the minority charge carriers are holes. So this is the way of representing PN junction diode simply, instead of drawing this schematic diagram. So we can simply represent this PN junction diode by using this symbol. So this PN junction diode has two terminals, one is anode and the another is cathode terminal, and it is represented by using an arrowhead followed by an bar, and then this will indicate the direction of the current flow. So this will indicate the direction of current flow. So this is called it as an arrowhead, and this is called it as an bar. So the arrowhead represents the direction of current, from anode to the cathode. bar represents it is an obstruction to direction of current. So that is no current flows from cathode to the anode. So diode is an unidirectional device. So that is the current can flow only from anode to the unidirectional device. Unidirectional device. And whenever if we are using for the practical purposes, the diode is represented or it is manufactured like this. The entire semi diode, it is enclosed with a case of black color. On the one side it is having some silver core. So the side of the silver core, which is the terminal cathode, and the other side is the anode terminal. So by using this we can identify which terminal is anode and the cathode. This is how the PN junction is formed and its symbol. Then this PN junction diode can be operated in 3 different modes or can be biased in 3 different conditions. One is the no bias condition, and the another 2 are forward bias condition, and third is reverse bias condition. Forward bias condition and reverse bias. In the no bias condition, no external power supply to the PN junction diode. So that is called it as an no bias condition. Under no bias condition, how the PN junction diode will work. So you can observe on the P side you have the majority charge carriers as holes, and the N side majority charge carriers are electrons. So if you observe on the P side you have more number of holes, and similarly you can observe you have the less number of holes on the N side. So that is on the P side and on the N side the concentration of holes and on P side is more, on the N side is less. So it gives you the non-uniform density of holes on the P side and on the N side. Because of this non-uniform density, the holes that can move easily towards N side, because of diffusion mechanism. So the diffusion mechanism happens when there is a non-uniform density on the material. So in the case of PN junction diode, so P side you have the more number of holes and the N side you have the less number of holes. So these holes they will move towards the N side. Similarly, you can observe for the electrons. Similarly, it can also be applicable for the electrons. Electrons are more on the N side and they are less on the P side. So that is again you have the non-uniform density of electrons. They are more on the N side and less on the P side. So again these electrons they can also move towards the P side. So these holes they are moving from P to N, and these electrons they are moving from N to P. So this is entirely we will call it as a diffusion. So this diffusion happens only because of non-uniform density of charge carriers inside the material. So while moving the holes from P to N side and electrons from N to P, so they will these holes, they are ready to accept one electron. Similarly, the electrons are more on the n side, they are ready to occupy that hole. So while diffusing from p side to the n side of the holes and electrons from n side to the p side, so they will be covered by these holes. So now nearer to this junction, whenever these electrons they are combining with the holes, then this atom is donating one electron. This atom is donating one electron. So these ions, they will combine with these holes, with these electrons. So nearer to the junction, so we will have only the ions. We have only the ions. So these are the, initially they have holes on the p side, and these except donor atoms, they have one electron, they are ready to donate. So now they are, because of this diffusion, these holes combine with the holes and these atoms become a acceptor and donor ion. So this will become donor ions and this will become acceptor ions because of recombination of both holes and the electrons. So now nearer to this junction, you have the more number of ions, there are no any charge carriers. So nearer to this junction, you have more number of ions, so they are called it as an immobile carriers, or we can also call it as an depleted charge carriers. So nearer to this junction, we have only the ions. Either on the p side you have the acceptor ions, and the n side you have the donor ions. So these are called as an immobile charge carriers or depleted charge carriers. So then because of these ions which are present on the p side or on the n side, so you can observe on the n side you have the more number of donor ions. So these donor ions have the positively charged. So this n side it is positively charged, and the p side it is negatively charged because of acceptor ions. So this will form one dipole. So on the p side you have the negative charge, and the n side you have the positive charge, which forms a simple one dipole. So because of the formation of this dipole, so it will give you the electric field, and this electric field is oriented from n to p, because n side is positively charged and the p side is negatively charged. So this electric field it is oriented from n to p. So because of this electric field, it will exert an electric force. So this electric force we can indicate it as an q into E bar. So because of this formation of this electric field nearer to the junction, it will give you the electric force, which is equal to F E is equal to Q into E bar. So for electrons, the F is equal to, so the charge of the electron is minus, so minus Q into E bar, and for holes it is F E bar is equal to charge of holes is plus Q into E bar. So you can observe the electric force on the electron. So for the electrons, the electric force is opposite to the electric field. So that is the on the electrons, the electric force is from, so the electric field is from N to P. So because of the electrons have the negative charge, so the electric force is on the opposite direction. So similarly on the holes, that is F into E bar is equal to, so the, if you observe the equation of electric force, so it is positive. So the direction of the electric force on the holes is from N to P. So after the formation of this charge, donor and the acceptor ions nearer the junction, so it will form an electric field, so which gives you the electric force. Now these majority charge carriers, which are holes on the P side, now they are trying to move towards the P side, but because of this electric force which is happening on the, which is generated due to this electric field, so these holes, they cannot diffuse further onto the N side. Similarly the holes, they cannot diffuse onto the P side. So you can observe the direction of the force. So the electrons are moving from N to P, so the electric force is in the opposite direction. So these holes, they cannot diffuse once after this region is formed nearer to this junction. So this is region, we will call it as an depletion region. So once the depletion region is formed, then there is no chance of holes which are majority charge carriers on the P side, they cannot diffuse onto the N side. Similarly the electrons which are majority charge carriers onto the P side, they cannot diffuse to the P side once after the depletion region is formed nearer the junction, because of this electric force which is present in the nearer the junction. So the diffusion of these holes and the electrons stops once the depletion region is formed. Once the depletion region is formed, then, and you can observe the direction of the majority charge carrier current. So majority charge carrier current, it is from P to N. So the electrons are moving from N to P, so the direction is opposite, that is P to N, and holes are moving from P to N, the current direction is also from P to N. So this is for the majority charge carriers. Then you can also observe there are minority charge carriers are also present both on the P side or on the N side. So P side, the majority charge carriers are electrons, and the N side minority charge carriers are holes. So now you can observe, because of this electric field, so the electric force which is exerted on the electrons, which is also from the P to N. So the electrons are the minority charge carriers on the P side, and the electric force is also on the same direction. So these electrons, because of that electric force, they can move towards the P side from P to N. Similarly, holes which are the minority charge carriers on the N side, and this electric force, it is also from N to P. So these minority charge carriers, they can also move from N to P. So because of this electric force which was there in the depletion region, and the direction of the electric force is also from N to P for the holes, these holes which are the minority carriers on the N side, they can diffuse onto the P side. So because of which these minority charge carriers which are there on the P side and on the N side, they can also move from one side to the other side. So because of which, because of this electric force, the minority charge carriers, minority charge carriers are drifting from from one side to the other side. From one side to the other side. So because of which you can observe, so the minority carriers which are electrons on the p side, so the current direction is from n to p. Holes are minority charge carriers are n, they are moving from n to p. So the direction of the current for the minority charge carriers, so the minority charge carrier current is from n to p. So you can observe from here. So the minority carriers are electrons on the p side, they are moving from p to n. Holes they are moving from n to p. So the minority charge carrier current is from n to p. So the total current which is flowing is equal to the majority carrier current plus minority carrier current. Minority carrier current. In this case, the majority carrier current is from P to N and the minority current is from N to P. So if you have observed in any circuit, according to current continuity law, current continuity law, the current, the movement of charge carrier is in same direction, in any closed loop. So in this case, the majority charge carrier current is from P to N and the minority charge carrier current is from N to P. So both these two currents are in the opposite direction. So at equilibrium state, both the charge carrier current are moving in the opposite direction. The total current becomes zero. So under no bias condition, so even though the charge carriers are moving from one side to the other side, but because of this majority and the minority charge carrier current are in the opposite direction, so we will get the resultant current as 0. So this is under no bias condition. We will stop here. In the next class